Let's say you have a piece of code. You can run it, maybe with some tests, and you can read it and think about it. But have you ever wanted to know for sure something about your code that isn't directly in the code? Does this program ever crash? Does it always return numbers between 50 and 100? Does it loop forever? These are things that testing might tell you aren't true by, say, getting your program to return 103. But no reasonable amount of tests can tell you that it's always true. It sounds to me like you should just write a proof that shows this. I don't want to. Proofs are gross. I'm a code person. I write code. What if you could write code that already is a proof? Hi, I'm Sanchez-Stern, a PhD student at UCSD. Actually, proofs and programs aren't that different. They can both be clearly wrong sometimes. A proof is clearly wrong when one of its steps doesn't follow logically from the previous one. And a program is clearly wrong when it tries to do something basic that doesn't make any sense, like accessing a variable that doesn't exist. One of the main tools we use to tell us whether or not our code is right is a compiler. And there are lots of bugs your compiler can tell you about in advance, before you run the code. For instance, let's look at this program. It's, well, wrong.
Computer says no.
But why exactly is it wrong? How does the compiler know? Well, to answer those questions, we're going to have to talk about type systems. A type system takes values in your program, like the number 1 or the word foo, and gives them a category called a type. So the number 1 would have the type integer, and the word foo would have the type string. It also gives types to all the operations you can do on values. So adding 2 integers is an integer, and adding 2 strings is a string. But there's no type for adding an integer in a string. So if your compiler sees something like foo plus 1, it knows it can't continue. This is called a type error, and it's one of the main ways our compiler can tell us if our program is wrong. Some language compilers will tell you about more errors before you run the program than others. For instance, Python, before you run your program, will tell you if you forgot to close a parenthesis, but not about expressions like foo plus 1. We call languages that do, like Java, statically typed, because they check the type of the values and their operations before you run the program. But there are still some errors the Java compiler won't tell you about, like if you try and access items in a list that don't exist in the list. So can we make a programming language that can tell you about more problems before you run a program than Java can? Enter William Alvin Howard and Haskell Curry, 2 American mathematicians who studied proofs and computations, or as we non-mathematicians call them, programs. Together they made a series of discoveries that show that the two are more similar than we thought. Around this time in the early 20th century, other mathematicians were also floating around these ideas, but Curry and Howard were the ones to really develop it into what we know today as the Curry-Howard correspondence. So what is the Curry-Howard correspondence? Well, it says that type systems, like those you'd find in Java or C, are actually equivalent to logical systems, like propositional or first-order logic. That means for everything in the type system, there's something in the logic that matches it, and vice versa. To see how that works, let's think about types and what they mean in a different way. Let's say I don't know if any numbers exist, and then you show me a number. You just proved to me that there are numbers. If we wanted to write this down, we might say that the statement, there are numbers, is proved by the number you just gave me. In fact, there are lots of proofs of there are numbers. 4, 5, 10, and every other number. Starting to look familiar? If every number is a proof, then we can change our question from there are numbers has a proof to the set of numbers, which is the int type, has a value in it. We can even put more than one of these together. For instance, if you give me the pair 3 foo, you've shown me that the type pair of integer and string isn't empty. And because of the way pairs work, I can get 3 or foo out of that. So you've shown me that numbers exist and strings exist too. Notice that? The type pair of A and B is equivalent to the logical statement A and B. You're probably thinking that's nice, but these are pretty boring proofs. We want to prove interesting, important things about our programs, not just whether there are any strings in existence. For instance, we might want to define things like dictionaries and show that they do the right thing. So something we'd like to be able to show is this, which says that if we set x to y in our dictionary, and then we get the value at x, we get y back, which is, some pretty normal dictionary stuff. To prove things like this, we're going to need a bigger boat. That is, we're going to need more types. In our world, anything we want to say logically is a type, and proofs of that thing are values of that type. So if we want to prove that two things are equal, we need to find something of the type A equals B. Whoa. Weird, right? Luckily, equals is just a symbol, so we can give it whatever meaning we want. So all we have to do is think of a type that doesn't do anything weird when we start thinking about it as equals. If we're going to build such a type, what would it look like? Well, we know it'll look like A equals B for some program expressions A and B. And we know that we should always be able to get the equality A equals A, or anything equals itself. Since we always want to know that anything equals itself, we can say that there's a value, reflexivity A, which always has the type A equals A. And that's it. That's our definition of equality. Reflexivity A has the type A equals A. It may not seem right away like this is enough to tell us all things we want to know about equality, but at least it's not going to tell us anything about equality that isn't true. If reflexivity is the only way for me to build an equality, then if you give me something of the type A equals B, I know that A and B must really be the same. One of the nice things about having equality as a type is that we can start to write functions whose arguments have an equality type, like this function. The function takes as input something of type A equals B, as in a proof that A and B are equal, and something of type B equals C, and returns something of type A equals C. It's going to be hard for us to call this function in our code because we can only produce equalities of type A equals A, reflexive equalities. But because our types of our programs can tell us things without having to run the programs, that's okay. We still haven't talked about one crucial property of types, that they don't change when you run things. So if my type system says that foo plus bar is a string, then when I run that and get the result, foo bar, it should still be a string. Now that we have program expressions in our types, it turns out the same thing is true on the other side of things. If I have a type that includes foo plus bar, I should be able to replace that with foo bar without changing things. This ends up being a really powerful tool for reasoning about types, especially when it comes to equality. It means that if I have something like reflexivity 1 plus 2, which has type 1 plus 2 equals 1 plus 2, I can also say that it has type 3 equals 1 plus 2, or even 3 equals 3. Because programs are, by their very nature, something we run, we get extra power in how we reason about them. Types like this equality are not something you can write down in Java, because the type talks about values, program expressions like A and B, instead of just categories of values. These types are called dependent types. With the power of dependent types, we can prove all the things. Let's say you're writing a piece of code that is supposed to sort a list. If your programming language has enough types, you can write a proof about that code and give it the dependent type, the list returned is always sorted. The computer and the compiler can check that type, and by extension, the correctness of your list sorting code. In effect, the type programs you write down let you explain to the computer why something is right. And if you can get the compiler to accept it, then you know that it really is right, at least given the right assumptions. And once you've done that, you can compose smaller components that you've proved things about into larger components, and eventually get whole software projects with formal guarantees about their correctness. For instance, Concert is a proven correct C compiler. C compilers are usually huge projects with millions or tens of millions of lines of code, all developed over months and years. Unlike Concert, we could do this with other projects, even bigger ones like operating systems. And all thanks to Curry and Howard. If you like this video and want to learn more about the theory and practice of tools for programming, make sure to check out the UCSD Progsys YouTube channel and subscribe.